All right, guys, before we get more into torque, specifically torque that's not at equilibrium, it would be helpful for us to just quickly review rotational kinematics. So basically just kinematics when objects are moving in a circular motion. All right. So we might be pulling in some of our strategies from two-dimensional kinematics and projectile motion, right, into what we're looking at with circular motion. Right. So, for example, when we look at like a CD, right, that's spinning around. I don't know. Do you guys even know what a CD is? Anyways, right, when it's rotating about a center point, it follows a circular arc. Right. So there's a few things that we can define. Right. We have we call S. This is our arc length. We have our radius, and then we also have our rotational angle. All right. So let's define these. Right. Okay, I'm going to use a different color. All right. So the rotational angle is the amount of rotation and is analogous to linear distance. All right, so when I think of distance d or x, right, this is going to be the same as rotational angle, which is defined as delta theta, or change in rotational angle. We define the rotation angle theta to be the ratio of the arc length to the radius of curvature. So put that into words, right? So our change in rotational angle is equal to the arc length divided by the radius. So again, let's just define these clearly. Theta is rotational angle. S is arc length. R is radius. And just remember, right, when we're looking at a full revolution, we can define that as 2 pi. All right, so again, shouldn't be celebrating Pi Day, we should be celebrating Tau Day, which should be June 28th. All right. So we're talking about kinematics, right? We're talking about our different variables that are analogous to these rotational variables. So for example, we're talking about velocity v, that is going to be analogous to omega, right, which is our angular velocity. And this is a measure of change of the rotational angle. And we can define this mathematically as omega. So right, it's not a W, it's omega, so it curves a little bit more inside. Right, it's going to be theta divided by time. Which we could also divide, or define this as our arc length divided by radius times time. And if you remember, you can kind of derive this further, right? We know that distance divided by time, right? This is analogous to this, which means that we could also define this as linear velocity divided by radius. Now note, right, when we're talking about linear kinematics, when we're talking about velocity, we use meters per second. In this case, right, we define our distance in radians. So our angular velocity would be rads, or radians per second. So let's plug all this into a example problem, right? So we got a wheel. It has an angular velocity, right? It also has a linear velocity. Linear velocity is, if we derive this, our linear velocity is going to be defined as angular velocity multiplied by radius. All right. So let's plug this in. We have an angular velocity of a 0.3 meter radius car tile when the car travels at about 54 kilometers an hour. So this can be worth remembering, right? If we want to convert this into meters per second, we divide 54 by 3.6. This gives us 15 meters per second. All right. So we're trying to calculate angular velocity. We're going to plug it into our formula. All right. We know the linear velocity and we know the radius. All right. Our linear velocity is 15 meters per second. And our radius is 0.3 meters. So our angular velocity is going to be 50 rads, or radians per second. All right. Next, we're looking at what would the angular velocity be for a car traveling at the same speed that had tires that were 4 times larger. All right, so before solving this, what we want to look at is we just want to look at some relationships in this formula. All right. We see that angular velocity is equal to velocity over radius. What this means is that angular velocity is proportional to the inverse of the radius. Let me make this clear. Proportional to the inverse of the radius. So, for example, right, we know that if angular velocity 1 is equal to velocity 1 over r1, right, this equaled 50. Angular velocity 2, right, which is for this question, is equal to, right, same linear velocity, but in this case is going to be 4 times our initial radius. So remember our proportions. It's going to be 4. End up with 12.5 rads per second. All right, so key thing here, don't confuse the proportional sign to the angular acceleration sign. The angular acceleration sign is alpha. It can be confusing, right? So it's not the Latin letter A or the English letter A. It is the Greek lowercase alpha. That is the term or the symbol we use for angular acceleration. All right, and this is going to be the rate of change of angular velocity. All right, so we speed up the circular motion of a car, right, or a wheel, or a circle. Right, this is going to be angular acceleration. Right. And we can define this formula as alpha equals change in angular velocity, omega, divided by time. And just like in kinematics, right, our units are rads per second squared. Again, the nice thing about this is a lot of our formulas are analogous to each other in circular and linear motion. All right, so quick question here. We have a student puts their bicycle on a stand, starts the rear wheel spinning from rest to a final angular velocity of 250 revolutions per minute in 5 seconds. Right? Our goal is to calculate the angular acceleration. Again, we're trying to find the amount of radians in 1 revolution. So let's do a couple quick conversions. So first thing we want to do is we want to see what is the change an angular velocity, or what is the velocity? So we're given 250 RPM, which we can define as revolutions every minute. So 250 revolutions every minute. All right, so let's convert. All right. A revolution is equal to 2 pi, and a minute, do this in multi-steps, right? 1 minute over 60 seconds. All right, we do some canceling out. So we end up with 250 times 2 pi over 60, which leaves us with 26.18 rads per second. All right. Now let's figure out alpha, or the angular acceleration. All right, so we have delta omega. All right, our change in angular acceleration, the final was 26.18. The initial was 0 because we started from rest, and the time was 5. Okay, put this all together, and we get about 5.236 rads per second squared. All right, part B, if they slam on the brakes, causing an angular acceleration of negative 87.3 rads per second squared, how long does it take for the wheel to stop? Again, in this case, same formula. In this case, we are solving for time. So you want to isolate time because that is our goal here. And that's simply going to be velocity over angular acceleration. We're basically reversing because now we know that our final velocity is now our initial, and we're coming to a stop. Okay, and our angular acceleration is negative. So notice that these should cancel out because time should be an absolute number. It should always be positive. Time cannot be negative in this sense. That's pretty easy, right? This just becomes 0.3 seconds. All right, so we're going to talk a little bit about the connection between circular motion and linear motion here. All right. So if an object experiences an angular acceleration, right, so the wheel or circle or whatever it is, right, is going to be increasing its angular velocity, right? We know that the velocity of any point on the object must be increasing or decreasing. The linear acceleration is tangential to the path of rotation. And therefore, we use the symbol AT, right? So this represents tangential acceleration. All right. So let's define this mathematically, right? I'm going to say AT equals change in velocity over time equals change in angular velocity times radius divided by time equals alpha R. Try and see if this works. Now, a couple things here to notice. of kind of how we derived all this. First off, let's just define that AT, or tangential acceleration, right? This is linear acceleration. Right, that's what this is, right? Acceleration tangential to the circular motion. We know change in velocity, right? This is linear velocity. And we know that defining linear velocity, V equals omega r, right, which is where we get to the next equation. We also know that angular acceleration, or alpha, is equal to omega over time, okay? Which is how we can simplify this formula up here to ultimately get to alpha r. So what we find here is that alpha equals tangential acceleration divided by r. There we go. That is so weird. Very annoying. All right, well, sorry, let me rewrite that real quick. T Okay. So we're looking at our line here, right? We see that tangential acceleration, right, is going to be, well, tangential to the path of circular motion. Same with the velocity. So angular acceleration, right, is tangential to the circle. And we learned previously that centripetal acceleration always points towards the center of the circular motion. Okay. So we see that there are some relationships between linear, also known as translational, and rotational motion. That's what we're going to get into here. So let's look at a little example here, right? We're going to kind of break this down in both like linear and rotational motion in some sense. All right, so we have a deep sea fisherman hooks a big fish, swims away from the boat, pulling the fishing line from his fishing reel. All right, so initially we could think about this as just, straight, right? The fish is straight in front of them. So this would be just linear motion. However, at this point, right, the reel is going to be accelerating, right, and unwinding. So we're trying to figure out what's going on with the reel itself. And so this is where we get into angular motion. So we're focused on the wheel itself. draw out our reel. All right, we know that our reel has a radius of 4.5 centimeters. So we convert that into meters, right? That's going to be 0.045 meters is our radius. All right, and we're trying to figure out what is the final angular velocity of the reel. Now, notice we have all these different kinematic equations over here, right? And they all are analogous to their translational or linear partners, right? So the nice thing about this is all our kinematic functions are exactly the same, right? The way we go about it is the same. Our steps are the same, etc. One thing that we would do a lot in kinematics is we would just write out, right? What do we know? What do we not know? So we can establish that, right? We just kind of create a little table. What's our angular velocity, the final one? What is going to be our initial? What's our angular acceleration? What is the rotational angle? What's the time? Okay. And just like in kinematics, right, we go through, we just can start by establishing what do we know, right? We know it starts from rest. We know the angular acceleration is 110 rads per second squared. And we know that time is 2 seconds. And here we can establish, okay, well, what is it we're actually trying to find out? In this case, we're trying to figure out what is the final angular velocity. So, once again, just like in kinematics, we look, all right, we don't need the rotational angle. So we're looking for a formula that has these 4 components, right? These 4 variables. Angular velocity final, initial, acceleration, and time. Right. We find that the one formula that has all 4 of those is this. Luckily, it's already set up for us. And from here, it's just plug and play, right? Pretty straightforward. All right, it's asking for B, at what speed is fishing line leaving the reel after 2 seconds elapses, right? So we're talking about, think about when a line is leaving the reel, how is that occurring, right? So we're focused on it's occurring tangentially, so this is more linear motion. So we want to focus on the actual velocity itself. All right, if you remember, one of the formulas we established is that the angular velocity is equal to velocity over radius. And if we're looking for velocity itself, the linear velocity, we could rearrange that equation to be this. We know that the final velocity was 220, and the radius is 0.045. End up with 9.9 meters per second, right? Is the velocity that the line is leaving the reel. All right, how many revolutions does it make? So let's use the rotational angle formula, right? So what's our starting initial plus 1/2 acceleration times squared. We know the initial velocity is 0, so we can ignore that. So we got 1/2, 110, 2 squared, 20 rads, and we're looking for revolutions, right? So we'll multiply this. All right, our revolution is equal to 2 pi. Get 35 revolutions. All right, and then finally, how many meters of fishing line come off? All right. So this is where we're getting a little bit into the arc length. All right. So in this case, we know that rotational angle is 220 rads, or radians, and our radius is 0.045. So our arc length, right, the total amount of line that's coming off is going to be 9.9 meters.